Okay, so here we continue with number 11. What dissolved species are present in a solution of Na2CO3? Well, this would fully dissociate to give 2 Na pluses and a CO3 2-. How do I know that? Well, sodium carbonate is soluble because the mainly soluble ions include the alkali group metals from group 1 right here, which are lithium, sodium, potassium, rubidium, and cesium. And so when those are soluble, it'll break up into the cation sodium and the anion carbonate. And so it exists primarily as Na pluses and CO3 minuses, which is letter A. Which ions are spectator ions in the following reaction? So this is a solid, BeOH2, so that won't dissociate. The H plus and the Cl minus will completely dissociate because this is a strong acid. This is aqueous over here, and all chlorides are soluble, and so the Be plus 2 and the 2 Cl minuses will be ions. And water is a pure liquid, which means it has to stay together. And so the only things that are exactly the same on both sides are the 2 Cl minuses. So those would be your 2 spectator ions that do nothing and do not react in the solution. Letter C. Be careful, this is a solid right here, and remember, don't split solids ever. Which ions are spectators in the following reaction? Same kind of question. This time you do split the strontium nitrate because it is aqueous and all nitrate salts are soluble. And this guy splits up into 2 Na plus and the SO4 2 minuses. On the right hand side of the reaction, notice that strontium sulfate is a solid. There's a little S down below it right here. And remember, all sulfates are soluble except for Fabs, and this is the S part right here. And then the sodium nitrate would completely dissociate to give you Na pluses and NO3 minuses. So the nitrates and the sodiums would be the spectator ions. Nitrate and sodiums, which is letter E. The balanced net ionic equation for precipitation of CaCO3 when aqueous solutions of these two are mixed. So if we're going to take Na2CO3 and react it with some CaCl2, we would swap the cations. You need to end up with some NaCl and then some CaCO3. You'd put a 2 in front of this to balance it. And then if you're going to write the net ionic equation, you could split, it says these are solutions, so you'd split both of those which are soluble. So you'd have 2 Na plus, CO3 2 minus, Ca plus plus, 2 Cl minus, then an arrow. The NaCl would split because that's soluble. And then the CaCO3 would be the precipitate. And if you didn't know whether or not NaCl was soluble, you could look in here and you see that all alkali metals are soluble and all chlorides are soluble. So the net ionic then would be the calcium and the carbonate, and the calcium carbonate over here, which if you look for the one that puts that together, it would be letter A, because the sodiums would spectate and the chlorides would spectate. Number 15, in which compound does sulfur have the highest, most positive oxidation number? So for each one of these, you need to determine what the oxidation number of sulfur is. In Na2SO4, we know that sodium would be positive 1 because it's in group 1 on the periodic table, and those are always plus 1. There are 2 of them. Sulfur is, I don't know the charge. Oxygen is -2 almost always, and there are 4 of those, and it has to sum to 0 because there's no number in the upper right-hand corner here, which means sulfur in this case would have to be positive 6, a pretty high oxidation number. Looking in letter B, in Na2SO3, sulfur would be positive 1. There are 2 of them. This is letter B now. Sulfur would be some oxidation state. Oxygen would be -2, and there's 3 of those, and it has to sum to 0. So this would be -4, which means that sulfur would be positive 4, not higher than positive 6. In H2S, if hydrogen was positive 1 and there were 2 of them, sulfur would then have to be -2. that once again is not higher than positive 6. S8, the elemental form of sulfur, is 0 because it's in its elemental form. And in SO2, sulfur would be some charge, oxygen would be -2, and there's 2 of them that would have to sum or add up to 0, which means that sulfur in this case would have to be positive 4. Once again, not higher than positive 6, leaving A as the species having the highest oxidation state number for sulfur of positive 6. Number 16, which element is reduced in the following reaction? So you have to assign the oxidation numbers, and then remember the thing that goes up in charge is oxidized, and the thing that goes down in charge is reduced. The assigning of the oxidation numbers is the tricky part. Fe is positive 2. Notice the 6 has nothing to do with assigning the oxidation number. Oxygen's -2. There are 7 of them, and 2 times 7 is equal to -14. The whole thing has to add up to -2 for the species in the upper right-hand corner. Chromium, there are 2 of them, and something times 2 plus -14 equals -2. So that means chromium in this case must be positive 6 on this side of the reaction. Hydrogen here is positive 1. Iron over here is positive 3. Chromium is positive 3. Oxygen -2 with hydrogen being +1. So the element that is reduced is the one that goes down in charge, and so chromium goes from +6 down to positive 3. So the reduced species is the chromium. By the way, they could change that question. They say which thing is oxidized, which you'll notice iron goes from positive 2 to positive 3. That goes up in charge, and so iron would be your oxidized species. Which element is oxidized in the following reaction? Assigning oxidation numbers once again. Silver is 0. Copper is positive 1. The nitrate species here would be -1. I apologize. The copper would be positive 2 right here because there's 2 of these -1 nitrates. Copper over here is 0. Nitrate over here, this species is -1, and silver would have to match it with a +1 charge. So notice, since I noticed that nitrate was on both sides of the reaction, I didn't have to break it up and figure out that nitrogen was positive 5 and oxygen was -2 in the species of nitrate NO3. I just took the entire NO3 piece and said that's -1. You can look that up on the back here if you don't remember that nitrate is -1. And then I matched that with the copper and said that copper has to be +2 because there's 2 of these -1 things in here. Anyway, the reason that I didn't have to break it up is because I can tell what's oxidized by doing that. Silver goes from +1 to 0, and so it goes down in charge and it's reduced. Copper goes from 0 to +2. It goes up in charge, and therefore it's oxidized. And so my oxidized species is my copper. In which of the following does the hydrogen have an oxidation number of 0? So right here, hydrogen in its elemental form would have an oxidation number of 0. Anything in its elemental form has an oxidation number of 0. And number 19, titration of Hi with 1 molar KOH. Swap the cations, HOH, put the cation first, Ki, balance the equation. That's step number 1 for any of these types of problems, is balance the reaction. Step number 2, once it's balanced, usually use the molarity triangle, but sometimes you use grams to moles to molecules, but convert to moles. Convert to moles is the key. So my moles here would be equal to the molarity, 0.5, times the liters, which 123.02 liters would be my moles of Hi. Put Hi in a position where it's going to cancel, and in step 3 we do a ratio of the substance we have to the substance we desire, KOH. And in this case it's really easy because the ratio is 1 to 1. 1 to 1 right here. And then lastly, convert to the asked for units. And in this case, they're asking for how many milliliters will be is required for that neutralization. for that neutralization reaction. And so 0.5 times 0.02 is 0.01. And then we'd take this 0.01 moles and we would divide it by the, we would multiply that by the concentration. By the concentration, because this is my number of moles, and I would divide that by my molarity to get the liters right here. I apologize, I think I said that wrong. I'm looking for the volume, because that's the units that they want to know, the milliliters. Cover up the milliliters with the finger, it equals moles divided by molarity. So I take my moles right here and I divide it by my 1 mole per liter that's given to me right here. So 0.01 divided by 1 means that there are 0.01 liters of the KOH solution that are needed. Notice all the units are given in milliliters. I have it in liters, so 1, 2, 3, that would be 10 milliliters are needed for neutralization, which would be letter E. So take a step back, look at those steps: balance, molarity triangle, ratio, ask for units, probably from the molarity triangle. Number 20, solution has a molar concentration. 2 liter sample of the solution is diluted to 0.8. What is the molar concentration of the diluted solution? So M1V1 is equal to M2V2. How did I know to use that equation? It has the word diluted in it. This is called the dilution equation. The initial molarity is 2 molar. A 0.2 liter sample, so 0.2 liters is my volume initial. It's diluted to a volume of 0.8 liters. Divide both sides by 0.8. I'll get the final molarity, or the final molar concentration, by taking 2 times 0.2, enter, divided by 0.8, enter. 0.5 molarity would be my answer for letter B. The solution is prepared by dissolving 20 grams of sodium hydroxide in the water to a total volume of 1 liter. The formula weight is, what is the molar concentration? So molarity is equal to moles divided by liters. First we need to find the number of moles, and there are 20 grams of NaOH. In 1 mole there are 40 grams, right? 40 grams per mole. So there are 0.5 moles. Put the 0.5 moles here on the top. Divide it by our number of liters here on the bottom, and it's a 1 liter solution. 0.5 divided by 1 is 0.5 molar solution, which is right here in letter A. Which is a weak acid? Hyber, Hickel, and Hi would all be strong. Hickelo and HNO3 is HONO. So the only weak acid would be HClO2. The balanced reaction below illustrates the combustion for methane for the next 3 questions. Which is closest to the minimum number of moles of oxygen gas that must be combusted to produce 44 grams of carbon dioxide gas? So start with your balanced chemical equation. Then take your 44 grams and convert to moles. And it's carbon dioxide gas, and CO2 adds up to 44 grams per mole if you add up 1 carbon and 2 oxygens. So 44 grams CO2. We need oxygen, so oxygen would be my new set of units. Carbon dioxide, go in a position where it's going to cancel. For every 1 CO2, there are 2 O2s. And it wants to know the minimum moles of oxygen, so I can stop right there. 44 divided by 44 is 1 times 2 is 2. So 2 moles would be the minimum number of oxygen gas that must be combusted, which is letter D. This combustion is a type of oxidation-reduction reaction. Which is the oxidation number assigned to the carbon atom in CO2? Well, oxygen has a -2 charge. There are 2 of them. You have to add carbon to it, and it must add up to 0 because there's no number in the upper right hand corner. Carbon therefore must be 4. Positive 4 is D. And lastly, 11 grams of carbon dioxide is produced. It's dissolved in 1 liter of water, which is closest to the molarity of carbon dioxide gas in solution. So molarity is equal to moles divided by liters. First, I need to find my number of moles of CO2. There's 11 grams divided by 44 grams in a mole. So that means I have 0.25 moles. Put your moles in a position on the top, and then divide that by our number of liters. 0.25 divided by 1 is 0.25. There would be 0.25 molar solution created.